Good to go? Cool. Well, thanks for coming to this talk. In this talk, we are going to talk about how you can harness the power of latest Kubernetes scaler, Karpenter, to scale, optimize, and upgrade Kubernetes. Before we get started, just wanted to give a shout out because if you have been in Venetian or Caesars Forum, I know it's a hike to come here. Both of us are coming from Venetian. It took us like over 30 minutes. My name is Rajdeep Saha. I'm a principal solutions architect working at AWS. I have been in AWS for around 5 years, and I help my customers onboard into Kubernetes as well as serverless. I'm also a published author and YouTuber. And I'm going to let my co-presenter introduce himself.
Thanks. I'm Ellis Tarn, principal engineer at EKS. I founded the Karpenter project 3 years ago, and yeah.
Excellent. So we have the founder of Karpenter with us. All right, thank you, Ellis.
I'll leave you to it.
Yep, let's get started. All right. So what are we trying to do? So basically, the job of cluster autoscaler is your application is running in one EC2 instance, and as it scales, we want to go to multiple EC2 instances. So zooming in a little bit, as traffic increases for your application, your pod scales using horizontal pod autoscaler. And those pods will get scheduled into the running EC2 instances. But as the number of pods grow, the existing EC2 instances will reach capacity. At that point, the traffic keep increasing, some pods will go to pending state. So in the previous version, with cluster autoscaler, we'll interact with autoscaling group, and autoscaling group, you have to configure different node groups, and tied to that autoscaling group, it will create EC2 instances. Karpenter removes all of that. Karpenter directly interacts with scheduler. For a minute, I thought my clicker was not working. Karpenter skips those cluster autoscaler and autoscaling group. Pending pods talk to scheduler, talk to Karpenter, interacts with EC2 directly, and provisions the EC2s for you. Because it is interacting directly with EC2 APIs, it is faster, flexible, and Kubernetes native. And you have a lot of controls to say what kind of EC2 instances you want to provision, AMIs, etc. And you do that using these two YAML files, node pool, formerly known as provisioner, and EC2 node class, formerly known as AWS node template. Okay. Scaling is, of course, the bread and butter of Karpenter, but the beauty of Karpenter is it does more than scaling. Karpenter can help you optimize cost. It supports diverse workloads, including machine learning and Gen AI, and it also helps you upgrade and patch. And throughout this talk, we are going to show you how it does that. So in summary, it helps you do a total data plane implementation. Karpenter is also open source and now a CNCF project. Just a couple weeks back, Karpenter was accepted into the SIG autoscaling. So let's say at this point you are like, all right, I want to adopt. What are the steps? So generally, first, you will do some evaluation, see what the features Karpenter provides, and then you will implement it. And after you implement it, you have to think about day 2 operations. So this will be the flow of our talk as well. We're going to start with the evaluation first. So how does a container scale? Like, what does it need to scale? CPU, memory, storage, network, sometimes GPU. And they run in EC2s. We don't make it easy. We have over 100 different types of EC2 instances, and depending on the instance type, you could have higher CPU to memory ratio, etc. So while this is a great advantage, it also complicates the instance selection and orchestration. And Karpenter helps you with all that. So remember I talked about node pool before. Think about this as a YAML file where you can define what kind of EC2 instances you want to provision. Anytime a pod goes to a pending state and the scheduler talks to Karpenter, it sees this YAML file. So let's go through this. In this YAML file, you can say what kind of instance you want Karpenter to provision. For example, instance family, C5, M5, R5. Instance size, not in nano, micro, small. And this is just a couple of examples. You can also do greater than, less than, all different kinds of operator. Also, you can totally skip this, and this is one of the superpower of Karpenter. It will automatically pick the best EC2 instance type based on your pod definition. You can also limit how many EC2 instances this node pool can provision. So as you could see on the bottom, this node pool will keep on provisioning EC2 till the number of CPU core reaches 100. Similarly, you can also specify what availability zone your EC2 should be provisioned, or you can skip this as well, and it will automatically pick the best availability zone. Next, you can put whether you want x86 EC2 or Graviton or purchase options such as spot on demand. This is a really good feature. If you want to mix in spot and on demand, you can simply say spot, comma, on demand, and Karpenter will always try to prioritize spot. Not only that, it is intelligent enough to know if spot is more expensive than on demand, it will provision an on demand instead. And as always, you can skip all of this. We wanted to make sure out of the box it works. And if you skip this last spot on demand part, it will provision the on demand if nothing is specified. Remember on the first slide, I said Karpenter is Kubernetes native. So what does that mean? Sometimes your Kubernetes workloads may be required to run in certain availability zone, certain instance type, spot, on demand, etc. How do you do that? You use mechanisms like node selector, node affinity, taints and toleration, topology spread, etc. Karpenter works with your pod's scheduling constraints. So let's try to understand that with an example, because I bet you will use this part a lot. On the left, we have a node pool, and this node pool saying any EC2 instance that this node pool provisions either has to be spot or on demand, or x86 or Graviton. And any nodes that this node pool provisions, these labels will be added. So if this node pool provisions a spot and AMD64, it will add the label carpenter.sh/capacity type spot and carpenter.io/architecture AMD64 to those nodes. What that means is, in your pod definition file, you can use those to schedule your pods. So in your pod definition file on the right, if you say, hey, this pod needs to be scheduled in a spot instance, Karpenter will provision a spot instance and schedule this pod. And in addition to that, Karpenter supports a bunch of well-known labels that's added to the nodes automatically. So you can use all these parameters to schedule your nodes. This gives you unparalleled flexibility to schedule your workload. How about user-defined taints, annotation, labels? Karpenter supports that as well. On the left, there is an example of a node pool where every node that's coming up, I'm attaching the label team:team A. On the right, you can use that to use this node pool to schedule the pods provisioned by this. So this is a good way to think about if I have 3 teams, maybe team 1 can be team 1, you put a label team 1, team 2, team 3, and for their pod definition, you schedule respectively. Spot interruption. Spot's awesome. Node pools can be configured for a mix of on-demand and spot, but here's the kicker. Karpenter has built-in spot interruption handler. You do not need to trap the spot interruption and use a bunch of other additional software. Karpenter tracks the interruption notice via an Amazon EventBridge event, and when you install Karpenter, you can give the name of this event bridge. Karpenter does the rest. It traps the 2-minute interruption warning, and then it spins up the spot instance. And it is not, you are not required to use node termination handlers. Also, going back to what I said before, if the spot becomes too expensive than on-demand, Karpenter will intelligently spin up an on-demand instance instead of a spot. So as we understand now, right, we have a pending pod. Pending pod has some scheduling requirements. And we have node pool. Node pool has also some constraints, and they interact each other. Then your EC2 node gets scheduled or gets provisioned. There are different strategies for defining node pools. You can have a single node pool throughout your organization. You can put a mix of Graviton, x86, bunch of other stuff, and every application uses that single node pool. Now, the middle one is pretty popular for multi-tenant environments, where you can say team A gets this node pool, team B gets this node pool, and the reason could be maybe team A needs to use some GPUs, or there is some security isolation that's needed, or different AMIs, or tenant isolation due to a noisy neighbor. Remember, we talked about how Karpenter, you can specify limits of how much CPU and how much memory. If some project needs to use a lot of hardware, but you want to limit them to a certain CPU or memory, you can use this strategy. And the final one is pretty cool. I like this one a lot. This is a weighted provisioner strategy. When your node's scheduling requirement overlaps with multiple node pools, you can assign priority to the node pools, and the higher priority node pools will be considered. So let's understand this with an example. So we have two node pools here. On the left, let's say you have signed up for compute savings plan or reserved instances, and you have instance category C and R, an instance CPU in 16 core or 32 core, and hypervisor Nitro. See the weight on the bottom? So the weight 60 will always be prioritized over anything which is less than 60. So as soon as a pod goes to a pending state and a new EC2 needs to be scheduled, on the node pool on the left will always be prioritized first. It will keep on provisioning EC2s till it reaches either CPU 1000 core or the memory 1000 GB bytes. After you exhausted and used up all your compute savings plan reserved instances, then the other node pool will kick in, right? Then the other EC2 instance types will come up. So this is an awesome way to implement a spot on demand ratio, reserved instances, etc. So now let's talk about cost optimization. This is one of my favorite features. Over time, your cluster may look like this. You have 4 EC2 instances running. The first one is really awesome, nicely bin packed tight. Last 3, not so much. A lot of underutilized nodes. With Karpenter, all you need to do is, in the node pool, put this consolidation policy when underutilized, and Karpenter will automatically bin pack the pods and get rid of other EC2 instances. Not only that, it is also intelligent enough. So let's say in this case, the last 2 EC2 instances are M5.extra large. Even if we consolidate these 2 pods into one M5.extra large, there will still be waste. So Karpenter will get rid of those 2 M5.extra large, provision a M5.large, and bin pack your nodes. So it's better selection of worker nodes and reduced cost. So if I combine all the features that we talked about, Karpenter combines the features of cluster autoscaler, node groups, node termination handlers, and descheduler. No longer you need to maintain all these different stacks. It creates a single software cohesive stack, so it reduces your overhead. So how does all this work under the hood? How does the magic happen? And to talk about that, I'm going to invite Ellis.
Thanks, Raj. So we covered what Karpenter does, and now we're going to talk a little bit about how it does it. We're going to go deep into a node launch, which is one of the most common things that Karpenter does, bringing new nodes to join the cluster. There's 4 major elements of this workflow: scheduling, batching, bin packing, and finally, the launch decision. Karpenter works in tandem with the kube scheduler, so you can kind of think of Karpenter as the back half, where kube scheduler is the front half. Kube scheduler is responsible for allocating existing capacity, and Karpenter launches new capacity when that existing capacity has no longer any space left. So in scheduling, there's a lot of things going on. Kubernetes has a very rich scheduling language for how do you run your containers, how do you run your processes on the underlying compute. The kube scheduler looks at pods and nodes, and it looks at a set of configuration, the resource requests, the tolerations, the node selectors, and the topology spreads. These all have to be considered by both the kube scheduler and the Karpenter algorithm. Karpenter has to maintain all of these concepts in memory to make sure that these constraints are being met when it's making its launch decision. The kube scheduler is doing a very similar simulation. So the kube scheduler looks at the requests. How many resources does this pod need? How much CPU? How much memory? It looks at tolerations. Which nodes are available? Maybe I can tolerate running on a GPU, or I can tolerate running on Spot. Which architectures do I need? Do I need to run on this team's compute or that team's compute? Can I do only ARM or only AMD? When it identifies that no capacity can meet these constraints, it marks the pod as unschedulable, which we call pending. Now we have a list of pending pods. But when do we decide to trigger a launch? If we just take a single pod and we immediately launch, then we'll get one pod per node. This could be really inefficient. We use what's called an expanding window algorithm to try to balance between launching capacity as quickly as possible and also making sure that we can bin pack effectively. We've chosen two values of 1 second and 10 second to try to make this trade-off. So what we do is 1 second idle period with a maximum of 10 seconds for batching. And I'll walk through a couple of examples here so you can understand what's going on. So in this example, we have a pod that appears in the cluster. The kube scheduler marks it pending, and at T0, we wait until T1, so a window of time when we don't see another pod, and we call that a batch. Then we flush that batch, and we do the rest of the launch algorithm. But what about in a more complex case? We get a pod, and then we get another set of pods without an idle second. And here, it's about half a second. When we do finally get that idle period, we take that batch and we flush it. And this is going to be a much more efficient bin pack. So depending on when the pods come into the cluster, we're able to make more or less efficient decisions. And this is just a fundamental trade-off of what we call online and offline bin packing. This is a classical area of computer science you can look into, and something that we think about a lot in terms of the heuristics and for how Karpenter works. After that batch, another pod can come in, and then we don't see anything else, so we flush another batch. And finally, 4 new pods come in later, and we flush another batch. But what about a case where there's a continuous stream of pods? In here, we don't have an idle 1 second, and so Karpenter, if you have a busy enough cluster, maybe you're running thousands of nodes, hundreds of thousands of pods, maybe we would just never act. We have to decide at some point, we're going to stop, we're going to do our best, and then we're going to keep looking at the remainder of the pods. In this case, we take an expanding window, we wait for 10 seconds, and we grab that batch. And then immediately after that batch, we take another with the remaining pods. Now that we have our pods, how do we decide which instance we want to launch? The first thing that we do is we discover instance types from EC2. We talk to the EC2 Describe Instances API, and we say, what is the entire universe? How much CPU and memory? What is available that can even be launched on EC2? Then we sort the instance types by cost, because that's what we're trying to optimize for. We want to launch whatever instances we can while minimizing for cost. Finally, we intersect the requirements. So we talked about all those scheduling constraints. We use a lot of set theory, set intersection. So we model the pod constraints, and we have to compare the pods against the other pods. So pod A and pod B may have different constraints. We have to factor in whether or not the set intersection of those are compatible with each other. And we also have to compare that to your node pool definition, which defines its own constraints. So we do a big set intersection of all of the different dimensions, architecture, operating system, as well as the size. so the amount of CPU and memory that's available on the instance. At the top here is scheduling and bin packing. We call these, they're kind of two parts of the same thing. Scheduling is the constraints, optimizing how tightly can we pack this within the constraints of the scheduling algorithm. And finally, we follow a reuse, grow, or create strategy. So we have these pods, and we create a virtual node, a node that we think we're going to launch given that set of instance types. We actually maintain the full list of available instance types for that node, and we say any of these instance types in this sorted order could be for this virtual node. And we take the first pod and we add it. As we add more pods, it changes the constraints. It changes the available instance types. Maybe those pods have instance type constraints, and so suddenly instance types are no longer possible to be used for this node. Maybe the CPU and memory is just now large enough that we have to remove instance types from the list of the available instance types for that node. So we go through all of the pending instances, and we try to make as large instances as possible while also making sure that it's as low as cost. As we go through, we can choose to reuse a virtual node by adding a pod to it, growing a virtual node, which is actually removing the smaller instance types of the available set, or we can create a new virtual node if there's a scheduling constraint that is invalid, say 2 pods have anti-affinity and just simply cannot run together. There's a whole bunch of complicated other things that go into here. We have to consider things like volume topology. Maybe your pod requires an EBS volume, and that EBS volume is only available in one zone. And suddenly, as you do a reuse for that pod, you now need to tighten the constraints with those volume topology constraints. We also need to think about the available volumes on the instances, how many volumes can even be mounted to this instance type, host ports, how many ENIs are available, what do the daemon sets look like, how big are the daemon sets. It gets really complicated really fast. The last thing to remember as we're doing this is we're not actually optimizing for utilization, and this is something that people think about or ask us about when they observe Karpenter in action, especially when using Spot. It's not about, I mean, obviously, utilization is a very valuable thing, and reservation is a really good output metric to know that Karpenter's doing its job. But what we're really doing at the end of the day is we're looking at the raw cost. And sometimes that means being at lower utilization, because what we care about at the end of the day is what is the cost of this compute? Just to double click on that point of how hard bin packing is, it's NP complete. We just cannot possibly hope to get it right. We use heuristics. They're getting more complicated all the time. If I were to describe to you exactly what we do, it would probably be different in a couple of weeks. We're making some major changes to this right now. There's dozens of dimensions to consider, so that just kind of grows the space even more. I mentioned that we're doing a similar simulation as the kube scheduler. The kube scheduler is doing a search problem, which is very similar. They're searching for which nodes of the known set can we use. We're not actually doing search because our space is so large. We could create new nodes out of nothing. We could reuse. We could grow. So we're kind of doing a generation problem rather than a search problem, but it's under the same constraints. There's some open questions where we've had to make judgment calls, like on preferences. Like if you have a preference to run in this availability zone, we try to respect it. We try to launch. But what happens if there's no capacity available in that zone? Maybe we could just stop provisioning and we could say, ignore the preference. Maybe we want to respect the preference and try to launch with that preference, but if it's not possible, then we just launch without it. There's a bunch of different types of preferences, and customers like yourselves have engaged in a very lively discussion on how we should treat preferences. So this is evolving all the time, and that kind of discussion also goes into impacting the complexity of bin packing. The last thing to note is Kubernetes is incredibly dynamic. If we were allowed to snapshot the cluster at a point in time and make a decision, by the time we've executed that decision and launched the instances, the cluster might have changed. Maybe these 5 pods at the top, one of them was deleted. Maybe there's a bunch more pods. Maybe a node was interrupted by Spot. We can never hope to be perfect, both for this change problem as well as the NP complete problem. So we try to make rapid heuristic-based decisions and make them as quickly as possible and as continuously as we can, so that over time we continue to optimize, we continue to solve the problem, so that things are not perfect, but they're always getting better. Finally, the launch decision. I mentioned that we have a set of available instance types for that virtual node. We try to shoot for 20 instance type flexibility, especially when using Spot. This is a magic touch for how we avoid spot unavailability or ICE, insufficient capacity exception, especially for exotic instance types like GPUs or smaller regions. Sometimes spot capacity is just not available. And so Karpenter's ability to maintain that high dimension of instance type allows us to talk to the EC2 Fleet API, say, here's all of our options, here's an allocation strategy to pick one. For on-demand, we just use lowest price. And then Fleet chooses which capacity is available on EC2 that meets these constraints. There's a little wrinkle here for spot allocation. There's a trade-off for spot, where if you just choose lowest price, you sometimes can get a very, very small capacity pool, a capacity pool that's almost unavailable. And it's a very high risk for interruption. So we use the price capacity optimized strategy, which is a EC2 Fleet API feature that allows us to say, give us the cheapest instance type, but don't give us one if it's about to be interrupted. So there's a little bit of a balance in there, and we rely on the Fleet API to make that trade-off. Now I'm going to hand you back to Raj to cover day 2 operations and onboarding for Karpenter.
Thank you, Alice. All right, so at this point, I'm sure you guys are thinking, wow, Karpenter is awesome. How I can adopt this and onboard into this? Well, we made it easy for you. You can install Karpenter Helm chart from AWS public ECR, and Karpenter runs on EC2 node as well. So do not run Karpenter on a node which is managed by Karpenter itself. Run Karpenter, we recommend running it on a 2-node node group, or you can also run on a Fargate. Now, a lot of you probably using cluster autoscaler today, and you want to migrate to Karpenter. So we have a step-by-step guide how to migrate from cluster autoscaler to Karpenter. And a lot of the customers use custom AMI for their AMI, and they have like an AMI pipeline. So good news is you can reuse most of the pipeline. Now on the last step of the pipeline, you are writing the new AMIs into ASG launch template. Instead, you write it on EC2 node class, or previously known as AWS node template instead. All right, now you onboarded into Karpenter. How do you observe the logs and metrics? So Karpenter, at the end of the day, is running as a pod, so you can simply run the commands that you check the logs out, such as kubectl logs, deployments as Karpenter, etc. Karpenter also emits Prometheus metrics, so you can install Prometheus and Grafana, and you can monitor pod startup latency, node utilization, and a bunch of other metrics. Okay, so now comes the day 2 operation. One of the big challenge of customer is, as the Kubernetes version is upgraded, or as AWS releases new AMIs, you need to constantly go and change those AMIs and constantly trigger the upgrades. Karpenter actually solves that problem using a concept called the drift. So let's understand drift first, and then we'll see it in action. So on the node pool, let's say you have a reserved instance type of m5.large. So all the EC2 instances that this node pool will provision will be m5.large. And after some time, you are like, m5.large is not ideal for my workload. I want to switch to c5.large. So at that point, you're running instances where m5.large, but the CRD, or custom resource definition of the node pool, says c5.large. So then there is a drift. Drift is a mismatch of either the CRD values to the machine or the vice versa. And when it happens, Karpenter automatically reconciles, so it will cordon the existing m5.large nodes, drain it, and schedule the pods into a new c5.large instances. You can enable drift in Karpenter global settings config map. It is auto-enabled after version 0.32. So let's see this in action, and we talked a lot about node pool. There is another YAML component, we call it EC2 node class. With node pool, we controlled what kind of EC2s, what availability zones, whether it's the x86 or Graviton. EC2 node class, as the name suggests, is more towards the EC2. What subnets are eligible to launch EC2s? what security groups needs to be attached to those EC2s, what AMIs should you be using for those EC2, and we support various different AMIs. You can run user data, define EBS, so on and so forth. Okay, so this is how Karpenter behaves when AMI changes. So let's say you are using AMI family AL2, which is the default AMI for a lot of you. Karpenter keeps on monitoring the systems manager parameter store. And all the Amazon optimized, EKS optimized AMIs are published, the name and IDs, into those parameter store. Karpenter finds out the latest AMI for the Kubernetes version you are running, in this case version 1.26, and creates the EC2s with those AMIs. So these are the actual AMI IDs for version 1.26 for US East 1. Now, let's say AWS releases a new AMI for the same EKS version with new security patches. When we release a new AMI version, AWS goes and updates the parameter store. So there is a new latest AMI which no longer matches your running AMI. So that's a drift. Karpenter will get that latest AMI and updates the worker node AMI in rolling deployment fashion. So it will create new EC2s with the new updated AMIs, drain the cordon and drain the older nodes, and migrate it here. What about Kubernetes version upgrade? If you update the EKS control plane, let's say from version 1.26 to 1.27, it's intelligent enough to know it is going to go check the parameter store. It will find out the latest AMI for version 1.27, and it will upgrade those worker plane nodes. So as you could see, this is zero touch and secure. You do not need to go run some pipeline, no need to run recycling command or etc. It's always using the latest EKS optimized AMI with all the latest security patches. Now, some of you may be thinking, oh, this is great, but what about custom AMI? So Karpenter supports custom AMI as well. You can select AMI using an AMI selector field in the EC2 node class. You could select using tags, you can select using name and account IDs, or simply by the ID of the AMI. If multiple AMIs satisfy your criteria, then the latest AMI will be used. If no AMI is selected, then no nodes will be provisioned. You can simply run a kubectl get command on your EC2 node class, and it will tell you what AMIs are discovered or satisfying the criteria that you are defining. It's a good way to test it out before you implement that in production. So let's take a look at the previous scenario, but now with custom AMI. So your EC2 node class, we are using the AMI ID 1, 2, 3, right? So all the EC2s that this Karpenter node pool and EC2 node class will provision is AMI 1, 2, 3. Now you have a new AMI, and you add that new AMI ID, AMI 456. Any new EC2 instance that is provisioned will be provisioned with the new AMI, AMI 456. But old nodes will not drift. Remember, we said drift is a mismatch between the CRD values and your machine. You still have AMI 1, 2, 3. So technically, it has not drifted. Now what if you want to migrate all those EC2 nodes into this new AMI, AMI 456? Well, you simply remove AMI 1, 2, 3. At that point, there is a drift. And then Karpenter will automatically upgrade those older nodes with the new AMIs. Karpenter also respects pre-registered AMIs. All right, so we talked about how drift can make your upgrading your data plane easy and zero touch, and we talked about consolidation before, how Karpenter bin packs and saves you money. So one of our large enterprise customers, Sentinel-1, they run thousands of nodes in one cluster. They adopted Karpenter drift for automatic upgrade of the nodes, and they enabled consolidation. Remember, it's just a flag. And by doing that, their containers started bin packing into underutilized instances, as well as Karpenter provisions new right-size instances. Because of that, they were able to save around 50% cost without any management overhead, literally a flag and an automatic drift feature. So now, how does all this work under the hood? So to do the deep dive, I want to invite Alice back on stage.
Thanks. We covered node launch earlier, which is probably about half of Karpenter's responsibilities. And the other half is what we call node disruption or node termination. Disruption is any event in the cluster that would cause us to remove a node. This is obviously a very scary action. You wanted those nodes because you wanted your pods to be available. And when we take away those nodes, it can cause risk to the cluster. So how do we protect against that? We rely on pod disruption budgets, and this is essential. You have to have these configured when using Karpenter or any other cluster autoscaler. Otherwise, your applications are not protected and may be disrupted faster than you can tolerate. Pod disruption budgets enable you to specify how many pods can be disrupted at a time and are a gate on the speed of disruption. You can also, for very sensitive pods, Karpenter supports an annotation called do not disrupt. If you set that, we will not attempt to disrupt a node for any pod that has that. You can also put that annotation on the node itself if you want to put a node to the side and make sure that Karpenter doesn't touch it. There are multiple types of disruption in Karpenter, and they're growing as we get more use cases, but we have a standard algorithm for reasoning about them. These are all types of node disruption. We talked about drift and consolidation, spot interruption, there's EC2 health events. There's a feature we have called expiration, where you can say that a node should only live for a certain amount of time. We classify these into two types of disruption, voluntary and involuntary. For voluntary disruption, this is something that we'd like to take action on, but it's not burning, it's not immediate. It's something that we have a choice about. For involuntary disruption, like a spot interruption or an EC2 health event, there's a slightly different algorithm. We try to move faster. We know that the node is going away, so we do whatever we can to make sure those pods are migrated off as quickly as possible. But those PDBs that you've defined may be violated in the involuntary case. In general, we try to minimize disruption. There's all sorts of side effects of disruption. Every time a new node comes online, every time new pods come online, you have to rehydrate any caches you have. You make a lot of DNS calls. So we just generally try to minimize disruption in the cluster. But we take action when we can based off of these voluntary and involuntary cases. There's a standard disruption workflow. The first thing that we do is we identify candidates. We'll talk about some of those methods later. We launch replacements, so we want to minimize disruption. We want to make sure that replacement capacity is available before we terminate the instances. Once those instances, those replacements are launched, we drain the candidates that we identified earlier by moving the pods, respecting the pod disruption budgets, using the evict API, and then finally, when those candidates have been drained, we terminate them. How do we identify which nodes are candidates? For drift, there's two types. One way is pretty easy. We can take a hash of the spec. So things like taints and labels, we do it on a per field basis, and we figure out, given your specification, what is a hash of what you asked for, and what is the hash on that node? And we can simply do a string compare and say, the specification has now changed from what the node launched, and we can now nominate that node as drifted. There's another kind of drift that can't be hashed. Things that Raj mentioned earlier, like discovering an AMI. That's something that's defined outside of the Kubernetes configuration, and we have to discover it. Discovering Kubernetes version, discovering AMI selectors. There's a bunch of different discovery mechanisms in Karpenter, so we periodically poll and compare those sets to do the discovered drift. We also have expiration. That one's super easy to compute. You can see here there's a creation timestamp on the node. We simply compare that with the duration that you've specified. If the node's too old, it's a candidate. Interruption, we subscribe to EC2 notifications. EC2 sends us notifications about spot interruption events, as well as EC2 instance health events. And so we can trigger an involuntary disruption, nominating a candidate when those happen. And finally, consolidation. This one's kind of hard, and we'll really go deep into it. So consolidation is a voluntary action. We want to lower the cost but we're trading off availability. How do we make sure that we don't disrupt pods, but we compress the cluster as much as possible? And this is, again, another one of our NP-hard problems. And it's pretty complicated. I'll do my best to kind of walk you through some examples here so you can get a sense for what are all the decisions that Karpenter's making. Again, we have this same problem. We're optimizing given the pod constraints and the node pool constraints. And in the code, we actually reuse all of the code, the whole simulation algorithm we reuse for consolidation with a couple of tweaks. Let's take this example here. This node is consolidatable, right? It's empty. Each box is a node, and then the pods are inside of it. This one's empty. This is a totally easy consolidation decision. But is this the best consolidation, or maybe a better way to think about it, a better consolidation decision? Is there something else that we could cheaply discover that could be better? What about these two? These seem well packed, right? But in the context of the whole cluster, maybe they could be consolidated as well, because there's capacity on the left, right? What about this upper left? Turns out the upper left could also be consolidated. You could move one of those pods to the right, and another one of those pods to the node below. Obviously, this is a gross oversimplification. There's a lot of pod constraints going on here. Again, volume topology, host ports, all those things are part of that simulation algorithm. In this case, we were able to consolidate those 3 nodes on the right and move those pods over to the existing capacity on the left. The decision is a fairly complicated heuristic. There's a bunch of concerns we're trying to address. We want to minimize pod disruption, of course. Disrupting pods, even though you have your disruption budgets, it's really not great to be running at the minimum of those disruption budgets. So we try to minimize the number of pods that get disrupted with each action. We also try to prefer older nodes. If we were to terminate very young nodes, then you can get what we call flapping, which is where a node is terminated, a new node is launched, and very soon after, another node is the same node is terminated. And the effect there is that certain applications are then disrupted more than others. And you can have an application that gets unlucky and gets disrupted over and over and over as the cluster state evolves. So we use node age to try to fight back against that problem. This is obviously extremely expensive to compute at scale. We're doing our best. These are all heuristics. And this is also evolving all the time. Let's take another case. This is a much less allocated cluster. In this case, we were able to terminate a huge amount of capacity and move all the pods onto an existing node. We call that an n-to-0 consolidation. So an n-to-0 means we're taking n nodes, and we don't actually have to launch any replacements. So back to that standard algorithm I mentioned earlier for the standard disruption algorithm, the candidates is actually, the replacements is just an empty list. So we don't need to launch any replacements. We can just start evicting immediately. Let's take this case. We have 5 nodes and 5 pods, but if we were to terminate, or 5 pods each, if we were to terminate any of the nodes, it wouldn't actually fit in the existing capacity. If you terminate that top node, you can schedule 4 of the pods, and you'll have 1 pod as a remainder. An n-to-0 consolidation doesn't work here, but we can do what we call an n-to-1 consolidation. So in this case, it was just 1-to-1, and we were able to identify, by looking at the cost of the EC2 instance type, that this instance type would be cheaper if we shrunk it down. And we were able to also simultaneously reuse the other available capacity in the cluster as part of the same move. Here's another one. This one is a n-to-1 consolidation again, but we're taking 2 nodes, and we identify that both of these nodes could be replaced. Again, you can imagine the complexity of this decision when you're reasoning about thousands of nodes and hundreds of thousands of pods. So, as you can tell, we're pretty excited about Karpenter. We've done a lot of development, but one of the things I love about the project is just how quickly it keeps evolving. The level of community engagement, the community contributions, the issues that are cut on GitHub. I love how Karpenter has an active online community and would invite you to join us, whether it's on Slack, at our working group every other week, or just cutting us a GitHub issue telling us how exactly we're not meeting your need, or a fix to our documentation. That's our talk. Thank you so much. Reminder, please complete the survey. It really helps us out.